Hello, welcome back to Earth Materials. In this lecture, I want to talk about the mineralogy of the transition zone and the upper mantle. So in the previous lecture, we were talking about the lower mantle, dominated by perovskite and ferropericlase, or perovskite structured materials and ferropericlase. First, I'm going to talk about the transition zone, and then I'm going to talk about the upper mantle. So the transition zone is dominated by polymorphic transition of olivine compositions. So I'll explain what all of this means, but olivine has a composition of FeMg2SiO4, and at shallow levels, the stable structure is the olivine structure, but as we go deeper and deeper into the mantle, the structure changes. It first changes to Wadsleyite, which is a spineloid structure. I'll show you what that looks like. And then Ringwoodite, which is a simple spinel structure. The densities change considerably as you go from olivine to Wadsleyite, and there's a bit of a change as you go from Wadsleyite to Ringwoodite. So let's think about this. If there's a big change in density, what also is going to change across that boundary? And you might think, well, seismic velocity is going to increase. Not so much because density increases, but because the physical properties of the minerals are also changing in concert with that. And that's what gives rise to this 410-kilometer seismic discontinuity. So this one is the olivine to Wadsleyite. So here's our seismic velocity increasing with depth. And there is a change in here as you go from Wadsleyite to Ringwoodite, but the big change is at about 660 kilometers discontinuity, where Ringwoodite, spinel structured olivine, and Garnet change to the much denser structures of perovskite structured material, bridgmanite, this calcium silicate, and ferropericlase. Now, olivine is an important mineral because it dominates the upper mantle. The general composition is A2BX4. So for forsterite, it would be Mg2SiO4. And although the compositions are quite different, it is in some ways analogous to spinels, which have 3 cations and 4 oxygens. And this will become important for understanding what happens to olivine structure as pressure increases. The A site is an octahedral site, so that takes metals, and the B site is a tetrahedral site, which takes silicon. If you remember how oxygens pack, there are 2 different types of sites. There are octahedral sites, and then there are tetrahedral sites. Now, they aren't all occupied in this mineral. It turns out there are chains of occupied octahedral sites, and then there are isolated silica tetrahedra. These don't actually link up with each other. So here is an image that shows these octahedral sites. You can think of it as either a zigzag chain going off like this, or you can think of it as a single central chain with a bunch of octahedra hanging off on the different sides. And it's actually better to think of it that way because these sites all behave similarly, and these sites behave similarly, but they're slightly different from each other. And it turns out that the interior sites of these chains, they're a little more distorted and they tend to prefer iron. The silica tetrahedra connect up the different chains. So here are silica tetrahedra, one pointing up, one pointing down, that link these chains together. But the silica tetrahedra themselves are not connected, so they are isolated. So this is why olivine is an island silicate or orthosilicate. At high pressure, olivine is unstable and instead forms a spinel or spineloid structure. So Wadsleyite is a spineloid structure and Ringwoodite is a spinel structure. So here's the structure of olivine that we were just talking about with these zigzag chains linked together with these isolated silica tetrahedra. In Wadsleyite, there are also zigzag chains that run through here, but they're connected differently with the silica tetrahedra. And if you look at these silica tetrahedra up close, then you'll see that there are actually 2 of these connected. These are pointing down two over here pointing up. And so they go along in pairs. The Ringwoodite structure is quite different. It has these magnesium octahedra, just like we see in olivine and wadsleyite. But these blocks of octahedra are connected with these silica tetrahedra, and these extend in all three dimensions. And it turns out this is a Spinel type structure, and it is much denser than the olivine structure. So, quick question here. If we think about wadsleyite, what type of silicate is it? And the answer is it's a bow tie silicate. So the two silica tetrahedra are connected together to make that kind of bow tie shape. If we look at their stability, this is now a pressure versus composition diagram. So this is a binary composition diagram, has magnesium silicate on the left, so this would be forsterite in the olivine field, has iron silicate on the right, so this is phaolite on the right. Most of the mantle is about FO90, 90% forsterite. So if we look at that composition, we find that there is a transition where olivine changes to wadsleyite structure. That's at about 410 kilometers. And then there is a higher pressure where wadsleyite inverts to form ringwoodite, the Spinel form. And of course, if we go higher and higher in pressure, then ringwoodite will eventually become unstable with respect to the lower mantle minerals, ferropericlase and perovskite. Here are some pictures of different composition wadsleyite, just for fun. So pure magnesium wadsleyite is colorless. And as we go to higher and higher iron contents, lower and lower magnesium contents, they become darker and darker. So that explains this block of minerals here, olivine, wadsleyite, and ringwoodite. But what about this other block over here, this majorite? Well, majorite is a garnet, and garnets have all kinds of very interesting chemistry. Most garnets that we see on Earth form rather shallowly, and they belong to what we can refer to as the Pyroxine group. So this is magnesium end member, iron end member, manganese end member, aluminous garnets. So these are all chemical substitutions of divalent cations on a cubic site. There are also the eugrandite garnets. That stands for euveravite, which is a calcium chromium garnet, calcium aluminum garnet, grossular, calcium ferric iron garnet, andradite. So majorite has a composition of MgSiO3, which is like orthopyroxene, but it's in the garnet structure. And so here, take a look at this. If I take 4 FeMgSiO3, so this is our orthopyroxene, and we put 3 of the iron and magnesiums in a cubic site, and 1 magnesium in an octahedral site, and silicon into an octahedral site, leave these 3 silicons in a tetrahedral site, then we end up with a garnet here. So we started out with 4 pyroxene, and we ended up with a garnet. But this is an unusual garnet, because what's going on, this silicon is in octahedral coordination. And if you remember from our discussion of perovskites, that's what's so unusual about them. That's what makes them so dense, is that silicon is in octahedral coordination. Chemistry of garnets, in general, it consists of 3 sites, an X, a Y, and a Z site. The X site is the larger cubic site, takes all these different elements that we've talked about. The octahedral site normally takes aluminum, but can take several other elements, especially magnesium and silicon in majorite, high-pressure garnet. And then the tetrahedral site can take silicon commonly, although it can also take aluminum and iron. So here is an octahedral site, usually filled with aluminum. Here's a tetrahedral site, usually filled with silicon. The tetrahedral sites are separated from each other, so it's an orthosilicate. And then if we look down here, it's a cubic site, but it's kind of distorted. So some people describe this as a dodecahedral site. It has 12 little triangles here. Other people, I usually think of it as a distorted cube. So it's like you took this face and you rotated it a little bit relative to that face. these are not even all the different garnets. These are just some of the more common ones up here that we run into, a few other ones down here. And they all differ in terms of their cubic site occupancy. So these are all aluminum silicate garnets. These all differ in terms of their octahedral site occupancy. Uvarovite, grossular andradite is what we were just talking about. There's another garnet called goldmanite. And then there are these weird garnets, magnesium ferric iron, calcium zirconium. If you put a +4 cation in an octahedral site, it has to charge balance. So now you're putting aluminum in a tetrahedral site. Not very common. Schorlemite, these are those titanium-rich garnets that put ferric iron into the tetrahedral site. And then here's Majorite with that strange magnesium in the cubic site, silicon in an octahedral site, silicon in the tetrahedral site. And I put this in here just to say that we talk about garnets, of course, in the earth sciences, but they're also important in some applications of materials science. So this one is a yttrium ferric iron garnet. So now, quick check. Transition zone, 410 to 660, is mainly composed of which of the following minerals? And the answer is A and B. What's important is that olivine changes its structure, but also the pyroxenes are not stable, that they invert to form the garnet structure, this majorite garnet. So at this point, I hope you would be able to explain how the different minerals change as we go from the lower mantle into the transition zone, especially in relationship to the upper mantle, which is what I'm going to talk about next. Okay. So we were just talking about wadsleyite and this majorite garnet. In the upper mantle, there is a transformation of olivine plus garnet plus the pyroxenes to olivine plus garnet. So there is this continuous transition of clinopyroxene and orthopyroxene into the garnet structure. And again, if we take 4 pyroxene here, it doesn't matter if it's a clinopyroxene or an orthopyroxene, we can turn this into a majoritic garnet as long as we make silicon octahedrally coordinated. So what we then see is that in the upper mantle, in shallow levels, we have olivine plus some garnet and some pyroxenes. And as pressure increases downward, the pyroxenes gradually transform into majorite. So as we hit the transition zone, olivine goes to wadsleyite. Then we find that it's mostly garnet and olivine. Now, pyroxene is an important mineral in the upper mantle. It has quite a complicated chemistry. There are 2 octahedral sites. There's a larger site. I usually think of it as an octahedral site, but it's much larger than another octahedral site. And these take somewhat different cations. This one tends to take larger cations. This one tends to take smaller cations, although iron and magnesium both occur in both sites. The tetrahedral site takes silicon and aluminum. And what's important about this structure is that the silica tetrahedra are linked up in individual chains. So here you're looking down on one of these chains. And here you're looking at the chain. So this is going back and forth. Here you can see it better. Back and forth and back and forth and back and forth as we go down that chain. Many times the way that these are presented is in terms of this overall structure here. So we have one of these back and forth chains, another back and forth chain, and then we have these octahedra. And that's represented here. So now we're looking at the back and forth chain of the silica tetrahedra, another back and forth chain of the silica tetrahedra with octahedral chains zigzagging back and forth. This kind of structure is what's called an I-beam. The way that the octahedral chains point defines what kind of pyroxene you have. So orthopyroxenes will have alternating pointing directions for the octahedra. So for this particular pyroxene protoenstatite, the octahedra point in one direction in this layer and the opposite direction in this layer. So point in this direction, that direction, this direction, this direction. And as a consequence, the A-axis is perpendicular to the chains, to the C-axis. Ferrocylite has a similar structure, but it has double pointing directions. So here, these are pointing in the same direction. Two of them pointing in the opposite direction, two more pointing in this direction, two more pointing in that direction, and so on. And so again, the A-axis is perpendicular to the chain direction, the C-axis. That's different in clinopyroxenes. In clinopyroxenes, the pointing direction of the octahedra is all the same. And what that does is it inclines the A-axis relative to the C-axis. And that's why we have orthopyroxenes and clinopyroxenes. It has to do with the pointing directions of the octahedra. And of course, this is one of the ways that we identify minerals in thin section, is which ones have parallel extinction, the orthopyroxenes, versus which ones have inclined extinction, the clinopyroxenes. Here is an image of that I-beam structure. So here are the silica tetrahedral chains. This is the intervening octahedral chains. And these are packed together in this kind of an array. So we have a TOT structure that kind of fit together. The weakest link in all of this are these M2 octahedra, which are between the I-beams. And if you link up the centers of these points among the I-beams, these define the cleavages of the pyroxene. And what you see here is that these cleavages are perpendicular to each other, or nearly perpendicular to each other for clinopyroxenes. This is a transmission electron microscope image, and what it shows is the electron density. Where it's light, the electrons are not very dense, and where it's dark, the electrons are very dense. And these light zones then actually turn out to be these areas between the different I-beams. So this is an I-beam, this is an I-beam, this is an I-beam, here's another I-beam, here's another I-beam, here's another I-beam, and so on. And so these light areas are where the mineral cleaves, and these are at 90 degrees to each other. So the chemistry of the pyroxenes can be pretty complicated. There are many elements that can go into this larger octahedral site versus this smaller octahedral site. And it turns out that this variation in chemistry creates a miscibility gap between the clinopyroxenes and the orthopyroxenes, usually the calcic pyroxenes and the iron magnesium pyroxenes. So here, for example, is a composition diagram. This is what's called the Pyroxine Quadrilateral: calcium, magnesium, calcium, iron, 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 magnesium, magnesium over here. So these are the calcic clinopyroxenes. These are the orthopyroxenes. Wherever this is purple, this is at very high temperature, then this pyroxene composition is stable. But wherever it's green, this pyroxene composition is not stable. A miscibility gap means that if you had a composition in here, so you took just the right elements and mixed them together to give you this composition and heated it up, what would happen is you'd actually separate out two different pyroxenes. You'd have a calcic clinopyroxene up here and an iron magnesium pyroxene down here. You would not have a mixed pyroxene composition. That kind of behavior, called a solvus or miscibility gap, is shown in this diagram here. So this is a temperature versus composition. So this is enstatite on this side, so that's over here. And diopside over here, that's this composition. And you're looking at the separation of these two compositions as a function of temperature. So what happens is, as temperature increases, these get closer and closer together in composition. And as temperature goes down, they separate out in composition. The enstatite becomes even more enstatite rich, less calcium in it. And the diopside becomes even more diopside rich, less enstatite dissolved into it. The region in the middle is where the two phases would coexist. That would be like this green region here. We can actually see this in slowly cooled pyroxenes. So this is a photomicrograph of a pyroxene that's cooled slowly. This is another image of a pyroxene, and this is a sketch of a pyroxene. These are the different lamellae in here. These bands represent different compositions. And what's really amazing about this is that these darker bands are orthopyroxene. These lighter bands are clinopyroxene. Okay, so they've separated out. And then even within the orthopyroxene, it's separated out little fine bands of clinopyroxene along with these darker, thicker bands of orthopyroxene. So there can be multiple stages of pyroxene separation as a rock cools. There are some other types of pyroxenes. There are the Sodic Pyroxenes. These form a mineral called amphicite, which is a solid solution mixture, mostly between jadeite and diopside with some Hedenbergite. Iron is in there. It forms only at high pressure and usually at the expense of feldspars. So this is an amphicite, which has a relatively high aluminum content. This is the mineral acmite. So this is a sodic pyroxene with ferric iron in it instead of aluminum. There's also a whole class of minerals called peroxinoids. They're very similar to pyroxenes, but they have a different structure to the silica tetrahedra. So here is a pyroxene arrangement of tetrahedra called an E chain, and there are these other arrangements of chains. So these are all, for example, pointing in the same direction. These point in a zigzag fashion. These are pointing in the same direction, but a different direction than this chain. So they're a little bit different. I think of them as being pyroxenes, but technically they're not. They're peroxinoids. Wollastonite, calcium silicate, and rhodonite, manganese silicate, are the two most common peroxinoids. So now, what is it that makes up the upper mantle of the rock? Well, it's mainly olivine, clinopyroxene, and orthopyroxene, but in addition to that, there is an aluminum-rich mineral. And exactly which aluminum-rich mineral you get depends on depth. At shallow depths, you get plagioclase. You've seen the composition of plagioclase. At intermediate depths, spinel is stable, and at greater depths, garnet is stable. And exactly what you see kind of depends also on what kind of crust is present. So oceanic crust is only about 7 kilometers deep, so it's conceivable that plagioclase is the stable aluminum phase. Normal continental crust is 40 kilometers deep. Normal continental crust is 40 kilometers thick, so at that level, we would expect spinel to be the stable aluminous phase. And under really deep crust like the Himalayan crust or the Andes, we might expect garnet to be the stable phase. So quick check, upper mantle, less than 410 kilometers. What are the minerals that you might expect to see? And the answer is all of the above. It kind of depends on where you are in the upper mantle. Some areas are going to have spinels, some are going to have plagioclase, and some are going to have garnet. We've talked about garnet already. I'm going to defer talking about plagioclase structure to another lecture, but I'd like to talk about spinel structure. Spinels are really common. They're an important oxide mineral. They have octahedral and tetrahedral sites, and we've talked a little bit about this. If you think about packing oxygens in a cubic array, so here's a cube, and we put oxygens in this regular array. There are points along the corners of these little cubes where cations are octahedrali coordinated, and there are points in the insides of these cubes where the cations are tetrahedrally coordinated. You can think of it as these oxygens can have a tetrahedral site, or if you put 3 oxygens mounted against 3 oxygens, there's an octahedral site. As I mentioned before, they have a generalized composition XY2O4, where X is the tetrahedral site and Y is the octahedral site. So there are 2 octahedral sites and 1 tetrahedral site. Now, remember what I was saying before about olivine. Olivine has 2 octahedral sites and 1 tetrahedral site. And so when we change olivine through Wadsleyite to Ringwoodite, Ringwoodite has the spinel composition. Now we've got the magnesium in octahedral coordination, silicon in tetrahedral coordination, but a different structure. It has a spinel structure, and that's what makes it so dense. We talk about normal spinels and inverse spinels. Normal spinels means that the same cation is present in the octahedral site, and there's a different one in the tetrahedral site. And inverse spinels mean that there are different cations in this Y site. So the classic example is that spinel is actually an inverse spinel. What does that mean? That means that this Y site that has two cations, the two cations are magnesium and aluminum. The tetrahedral site contains aluminum. Hercinite, iron aluminum oxide, is actually a normal spinel. So what does that mean? That means that the aluminums are in the octahedral site and iron is in the tetrahedral site. So here are several different spinel structured minerals: magnetite, chromite, spinel, hercinite, so on. And this one separates out what are the cations in the tetrahedral site, what are the cations in the octahedral site. And so here, if we look at chromite with iron in the tetrahedral site, two chromiums in the octahedral site, that's a normal spinel. If we look at magnetite with ferric iron in the tetrahedral site and ferrous and ferric iron in the octahedral site, that has an inverse spinel structure. One of the really interesting things that we can do with coexisting oxides is when we have magnetite and ilmenite together in the same rock. It turns out that we can estimate both the temperature and the oxygen fugacity based on the degree to which titanium is dissolved in magnetite and ferric iron hematite is dissolved in ilmenite. So here's the way this works. You measure the composition of an ilmenite and you identify how much hematite is in it. So let's say it has 5% hematite component. And then you measure the titanium content and you figure out how much of this weird olvospinel component is in it. And if it's 40%, so magnetite is 60%, then that tracks out this line on what is this? It's a log of FO2. FO2 is fugacity. It's essentially the pressure of O2 versus temperature. And where these two lines intersect for the magnetite composition and the ilmenite composition defines a temperature. So what would that be? Somewhere close to 700 degrees. And an oxygen fugacity, which would be 10 to the minus 18. The oxygen fugacity is important for distinguishing the degree to which iron is present as ferrous iron versus ferric iron, and that has all kinds of implications for mineral stability and melting. So having these coexisting magnetite and ilmenite pairs can be very helpful, especially in igneous rocks. Okay, so at this point, I hope you would have a general sense of the stability of aluminum-rich phases in the upper mantle, and then have a sense of the different structural and chemical differences between orthopyroxene and clinopyroxene. All right, thanks.